Okay, for question number 3, we have here a 70-kilogram man who is doing push-ups. We are shown in this diagram the position of his center of mass relative to his hands and feet. And it's 42 centimeters from his hand and 95 centimeters from his feet. We are asked to determine the support or normal forces that the floor exerts on each hand and each foot. So each hand and each foot, and we can ignore any frictional forces. Okay, so we are shown in this diagram here the weight force, which is acting at the center of mass. Okay. Obviously, we are being asked to determine the normal or support forces that the floor exerts on each hand and foot. So there should be a normal force on the hand provided by the floor. So that will be directed upwards, normal force on the hands, and normal force on the feet. It's also directed upwards. Okay, let's call that NF. All right. So we can ignore frictional forces. So there are no static frictions in this case between the hands and feet and the floor. So these are our 3 forces: the NH, normal, exerted by the floor on the hand, that's directed upwards; NF, the normal or support force exerted by the floor on the feet, which is directed upwards; and weight force, which is always directed downwards. Right. So we can calculate the weight force because we're given the mass, 70 kilograms. We do not know NH and NF. Right. So the next step is to choose the pivot point. And because we do not know NF and NH, a smart choice of pivot point would be either NH or NF. That way we can eliminate one of the unknowns. Right, so yeah, because we want to find both NH and NF anyway, yeah, force exerted by the floor on each hand and foot. Okay, why don't we first use NF as pivot and then NH as pivot? But let me just redraw our free body diagram and do the working here. Okay, so our free body diagram, that's the man. He's horizontal, so we can just represent him by this horizontal line. So again, when we're drawing free body diagrams for the purposes of finding the torque, the position of the forces is important. Okay, and so we have the weight force here, that's downwards, the normal force on the hand, that's upwards, and the normal force on the foot, on the feet, and F, that's also upwards. Right. So we are given the following distances. So the distance between the hand and the center of mass is 42 centimeters or 0.42 meters, and the distance between the feet and the center of mass is 95 centimeters or 0.95 meters. Okay, so we have our 3 forces. The next step is to choose the pivot point. Okay, again, pivot point is arbitrary. It's up to you to choose any point in your diagram where to put the pivot point. A smart choice will be to put your pivot point at the position of one of the unknown forces or at the position where you have more than 2 forces. Here, we don't have any point where we have 2 or more forces, but we do have 2 unknown forces, NH and NF. So why don't we first put, for example, the pivot point at NF? Okay, so once you've chosen your pivot point, the next step is to identify your lever arms. Okay, so lever arm, that's the distance from the force to the pivot point. So you see why it's important for you to choose first your pivot point before determining your lever arms, because your lever arm is measured from the force to the pivot point. So it's a perpendicular distance from the force to the pivot point. Okay, so from the center of mass to the pivot point, the lever arm will be 0.95 meters. Right, and then from the normal force on the hand to the pivot point, okay, you extend the normal force on the hand and draw a line that's perpendicular to the normal force on the hand towards the pivot point. That will be the lever arm between NH and the pivot point. So that will be 0.42 meters plus 0.95 meters. Okay. Which is equal to 1.37 meters. Okay, so once you have your forces now and your pivot point, you can now do your torque equation about the pivot point. Find the net torque about the pivot point, which is NF in our case, because we put the pivot point at NF. Okay, so recall the torque is equal to lever arm times the force. Okay, so let's consider NH, the force NH. Right, so NH has a lever arm of 1.37. So torque is equal to lever arm times the force. Okay, so considering the force NH, the torque will be 1.37 times NH. Okay. Next, determine whether the torque is positive or negative about the pivot point. So looking at NH, it's pointing upwards. So if it were to rotate the man about the pivot point, it will rotate the man in a clockwise direction. Right, and so clockwise will be a negative torque. That means that our torque for NH should be negative. So you add a negative sign there. So torque due to the force NH will be negative 1.37 times NH. Okay. Right, now for the weight force, the torque is equal to lever arm times the force, and the lever arm between the weight force and our chosen pivot point is 0.95 times the force W. Okay. Now looking at the weight force is pointing downwards, and so the tendency of the weight force, if it were to rotate the man about the pivot point, is a clockwise rotation. So if the weight force were to rotate the man about the pivot point, it will rotate it in the anti-clockwise direction, and anti-clockwise rotation means a positive torque. So the torque due to the weight force will be a positive 0.95 times weight force W. Right. So and finally, for the torque due to NF, that will be 0 because we put the pivot point exactly at NF, so the lever arm will be 0. So we now have accounted for all the torques due to all the forces. So it's just the torque due to NH and due to W that is non-zero, and they both add up to 0 for the man to stay in equilibrium. We are wanting to find NH, so we rearrange this equation to isolate NH by adding NH to both sides of the equation. I am able to cancel NH on the left hand side, and I'm left with 0.95 times the weight force on the left hand side and 1.37 NH on the right hand side. Okay, I divide both sides by 1.37. In order to isolate NH, I just flip this so NH is on the left side. Okay. Then I will be able to solve for NH because I'm given the mass of the man is 70 kilograms and weight is equal to mass times gravitational acceleration. So this weight force W is mass times gravitational acceleration. So this weight force will be 70 times 9.8. That's all divided by 1.37. So the normal force on the hands will be 475.69, and this is for both hands. Both hands. I want just the normal force on one hand, so I divide this by 2. To 337.8 newtons, or I can round that to 238 newtons. Just fix my 2. Yeah, so this is the normal force on one hand. That's the normal force on one hand. Okay, all right. So if you put your pivot point at NH, then what you will be able to find will be the normal force on the feet, okay, on both feet, and divide that by 2 to get the normal force on one foot. So again, it depends on where you put your pivot point. In this solution, I put the pivot point at NF, and therefore I was able to solve for NH. If you put the pivot point at NH, that eliminates NH, and you will be able to solve for NF. Okay. All right. Just for argument's sake, if you find the torque about the pivot NH, okay, so just for the case when we put our pivot point at NH, just to illustrate the point, so that's NH, that's the weight force, and that's NF, NF. Right, and we choose our pivot point to be at NH. Okay, our lever arms. Okay, the lever arm, due to the weight force at the center of mass, will be 0.42, okay, which is given. The distance here between the weight force and the hands is 0.42 meters, so that will be the lever arm between the weight force and the chosen pivot point at NH. And the distance, the lever arm between NF and our pivot point NH will still be 0.42 plus 0.95, it will still be 1.37. Okay. Right, so when we find the net torque about NH, okay, so let's do the torque due to the weight force. That will be lever arm times the force, so that will be 0.42 times the weight force. Okay, if you look at the weight force, it's pointing downwards, and so if it were to rotate the man about the pivot point, the tendency would be for the weight force to rotate the man in a clockwise direction, so that will be a negative torque. Right, so that will be a negative 0.42 times W, or weight force torque. See how your solution is different. Okay, let's do now the torque due to NF. So torque is lever arm times the force. Lever arm between NF and NH is 1.37. Okay, multiply that by the force, which is NF. Okay. Now if NF were to rotate the man, because NF is pointing upwards, NF will rotate the man in a clockwise direction. In an anti-clockwise direction, so that will be a positive torque. So you have the torque due to NF about the pivot point at NH will be a positive 1.37 times NF. Okay, right. And the torque due to NH will be 0 because we put our pivot point at NH, and so lever arm will be 0. Right, so we only have the torque due to the weight force, which is negative, and the torque due to NF, which is positive, and those two torques add up to 0. So you see how your equation is different depending on where you put your pivot point. Okay, if your pivot point is at NH, you have a negative 0.42 W. If you put your pivot point at NF, you have a positive 0.95 W. Okay. All right, so moving on and solving for NF. So we isolate NF. So NF by we isolate NF by subtracting NF on both sides and multiplying by negative. We have NF will be equal to 1.37 NF is equal to 0.42 W. Dividing both sides by 1.37, we have 0.42 W divided by 1.37. Right, so NF, again, W is equal to mass times gravitational acceleration. Mass is 70 kilograms times gravitational acceleration of 9.8, and everything's divided by 1.37. Okay, so plugging that into your calculator, you get a net force of 210 newtons. Okay, this is for both feet. Okay, so for 1 foot, you divide 210 by 2, you have 105 newtons for 1 foot. Let me just write that down here. Yeah, so that's for 1 foot. Right. Yeah, you can also solve for the net force on the foot, the normal force on the foot, by using the sum of forces, or you can use net force is equal to 0. Okay, so we have two forces that are pointing upwards, NH and NF. They should add up and they should equal the force that's pointing downwards, which is W. So NH plus NF should be equal to W, or NF should be equal to W minus NH. Okay, 70 W is 70 times 9.8. Subtract that to the NH that we got. Use the NH for both hands. And you should get 210 still. And still, that's for both feet. So NF is equal to 105 for 1 foot. So you see that you get the same thing by doing net force. So once you have NH here, you can do net force is equal to 0, and you get the normal force on both feet. By dividing that by 2, you get the normal force on 1 foot. Or you can do the torque equation, putting your pivot point at NH, you get the normal force on the foot NF, which will work out to be the same value as when you use net force is equal to 0.